Lately, with the arrival of winter, friends and acquaintances are increasingly asking me to assemble a car battery charger for them. I often make such chargers based on thyristors. They are practically eternal, work without issues in the cold, and have all the necessary protections. In general, they're indestructible things. I have plenty of transformers for building such chargers. However, there aren't that many compact and powerful thyristors. During this visit, I found a real treasure, a bunch of compact and powerful thyristors, all from one seller. Among all this stuff, there are also very powerful so-called tablet thyristors at 320 and 250 amps. I need such thyristors for a new project of comprehensive protection against overvoltage, short circuits, and overloads for a regular household network. In general, if you install such protection in your apartment, you won't have to worry about network voltage instabilities, overloads, or even wiring overheating. The system is still just on paper, but I hope to have some free time soon to work on it. There are also optothyristors 2142-80-8 with a full 80 amperes. Their voltage is 800 volts. There are also these tiny ones, also optothyristors, but for a lower current of 12 amperes. They are also suitable for a charging device. The feature of optothyristors is that they have an infrared diode inside, which controls the thyristor itself. The principle of a regular optocoupler. To ensure galvanic isolation, the control circuit from the high voltage part, no additional optodevices are required. All of this is already built into the thyristor itself. From the same person, I came across these thyristor modules MTT2-80-4 for 80 amps, 400 volts, with a pair of thyristors inside. If desired, one such module can be used to create an analog of a triac for full control of the mains voltage. These modules are conveniently mounted on a heatsink using a couple of screws. Based on them, you can assemble a current regulator, for example, for a welding machine. It can handle it without any issues, and there will even be some reserve. The other thyristors are not remarkable, except that they are compact and powerful. Such ones are much rarer than high-power thyristors. I also took 4 standard 10-amp diodes purely because they were on nice heatsinks. I have a bunch of diodes like that, but no heatsinks. Thyristors at 250 and 320 amps were sold at the same price of 400 rubles each, with no room for negotiation. And in principle, that's cheap considering that a new T133-320 costs from 2,000 to 4,000 rubles. However, on online marketplaces, used options can be bought for about 500 rubles. Small thyristors are literally priced like scrap, 80 rubles each, including 80 amp optothyristors. Thyristor modules were 450 rubles for a pair, and small optothyristors were included as a bonus, for free. Unfortunately, upon arriving home and checking, it turned out that the pair of 320 amp thyristors were dead, short-circuited on all fronts. It's a damn shame, of course, but at least there's a reason to break one open and show you the inside. We have 2 identical massive copper contacts, a cathode and an anode, separated by ceramic. Most likely, they are beryllium. In the center of one of them, there is another contact, again isolated from the main one by a ceramic insulator. This is the control lead, which is also spring-loaded. And here is a huge crystal, on which a breakdown is clearly visible. I forgot to mention that the current collection from the crystal is not done directly, but through some intermediate conductors made of silver. They cover the entire surface of the crystal on both sides. According to the specifications, the amount of silver in this thyristor is a little over 4 grams. And now, the most expensive purchase in the last 3 months. I stumbled upon this thing in such a condition, so unfortunately, I can't say exactly what this source is from. If you have any thoughts on this matter, please leave a comment. A huge aluminum case, or rather what's left of it. And inside, there are 2 power transformers OSU 04 kilovolt ampere. There were 3 transformers. I didn't take one, because the price wasn't very reasonable. Besides, I only need 2 transformers for my next project. In general, I want to make a semi-automatic out of this stuff. Possibly, based on the iron of the 2 transformers, one more powerful one will be assembled, or perhaps the transformers will be connected in parallel. Later on, they will need to be tested to understand what this hardware is capable of. On the front panel of the case, we have indicator lights, windows for circuit breakers, power terminals, and switches. Each transformer has one primary winding for 220 volts and one secondary with taps at 5, 36, and 42 volts. The cost is 3,000 rubles. Maybe that's okay, but for a flea market, it's a bit pricey. These transformers used to be cheaper. And now for the most interesting purchase during this period. A low-voltage professional soldering station made in the USSR, term it PM3670. These can now be bought on online flea markets for a couple of thousand rubles. I saw this station in a pile of junk, and at first, I even thought it was some kind of time relay or temperature regulator because the soldering iron was tangled in a bunch of wires. The station is very interesting because it is analog but highly accurate. It features full thermal stabilization. There is a temperature sensor inside the soldering iron. There is a separate submodule on the side for temperature control. In my opinion, the soldering iron is very convenient, considering the size and appearance of most Soviet soldering irons. I can't say for sure, but most likely, such soldering stations were used in radio factories and are designed for professional use. The tips for the soldering iron are replaceable, specialized, and of a non-standard shape. Unfortunately, in the pile of junk, I didn't find the tip holder or the tip itself, so we'll have to figure something out. At the front, there is a large switch that sets a fixed temperature value. There should be a sticker with the temperature ranges here, but as you can see, it has fallen off. Next to it, there is a variable resistor for more precise temperature setting within 2 degrees. The temperature range is from 140 to 340 degrees. I found almost all the missing pieces of this station. It was in a semi-disassembled state. I finished disassembling it at home, but naturally, all the parts were preserved. The worst part is that the station doesn't work. It doesn't work at all. The thing is, it's low voltage, and you need to supply it with alternating voltage around 36 volts, at a frequency of about 50 Hz, but the plug is a standard network one. An ordinary uninformed person will try to plug it into the network and get a bang. The protective fuse and the triac in this soldering iron have burned out. What else has burned out, I don't know yet. The control here is phase pulse-based using a triac. There is a separate transformer for controlling the triac. And the large transformer provides power for the control system. In general, since I really liked the station, I dug up some information about it and intend to release a separate video with a full historical overview and repair of the station. I think it will be interesting. I would love to use it. By the way, this piece of history cost me 300 rubles. That's all. A non-inductive, or non-induction, 60-watt resistor. Unlike its counterparts, it is not wire-wound, has no inductance, but it weighs a lot. It is perfect for use in pulse circuits and has massive terminals. The resistance of this specimen is 200 ohms. When buying it, I knew what I was getting it for. I will use it in a soft start system for a very powerful induction heating setup. And this video is also in the works. It's not exactly the best use for such a cool resistor, and may one comrade forgive me who made a load equivalent based on similar resistors. A powerful 30 amp shunt with a drop of 75 millivolts. Accuracy class 0. 5. Condition is perfect, costing only 50 rubles. I think the areas of application are clear. Shunts are never unnecessary. I have all sorts of unusual hobbies, like collecting retro transistors. I wouldn't mind paying a couple of $100s for a good specimen. But I also just love all kinds of tweezers, especially Soviet ones. By the word tweezers, I mean anything that extends the capabilities of our hands. Yes, this is my hidden hobby. If I search well throughout the house, I can fill a suitcase with all sorts of tweezer-like things. This time, I came across a set. Most likely, these are medical instruments. I don't know what these things are called, but I took everything that was there, although often, they just lie around my house. But for work, I use, at most, a dozen different tweezers, which I sharpen and temper for my needs. A spark gap protector. R35. This is a 3-terminal spark gap in a glass design, intended to protect the device from overvoltage. It came with its original socket. The breakdown voltage is on average 280 to 320 volts. The maximum current is 15 to 30 amps, pulse, up to 2.5 kiloamps. It weighs about 40 grams. It can operate in any position, and has a guaranteed lifespan of 50 breakdowns. However, during my experiments, it has already broken down hundreds, if not thousands, of times. As you might have guessed, I use it slightly for other purposes, specifically for high-voltage experiments. For example, at the moment, I'm playing around with an electrohydraulic shock setup. That is, this spark gap has to endure the discharge currents of large capacitor banks. And it is still alive and will continue to work until something better is found to replace it. After completing the filming of this video, I visited the flea market once more and dug up a bunch of cool stuff. But that's a whole different story. Rate this video, share it with your friends on social media. Also, I have an Instagram, not hinting at anything, just saying that it exists. And that's all from me. As always, this was Kazyanov K with you. Until next time, bye.